We are going to model an End Fed Halfwave antenna using MMANA GAL. So first we start the MMANA GAL application here. The program launches, and a few words about the program itself. We are using right now MMANA GAL Basic. You can contribute to the effort of the programmers by upgrading and paying for MMANA GAL Pro. However, for this exercise, we're just going to leave the freely available MMANA GAL Basic on the screen. Note that we have the menu bar up here. We have some quick icon access tools up here. And then we have our 4 tabs: Geometry, View, Calculate, and Far Field Plots. In Geometry is where we specify the geometry with x1, y1, z1, which we're going to leave at the origin, x2, y2, z2. Essentially, in 3 space, the beginning and end points for our antenna. In the view, we're going to go ahead and see our antenna. We can hold down the mouse and move it sideways, hold down the shift key, move it up and down so we can actually see our design a little bit better. In Calculate, this is where the main action of the program takes place. We're going to click on the Start button when we're done with our modeling to actually start the program to run the actual calculations. And notice here that we have the ground definition box right here. We're not going to select free space, perfect. We're going to go with real. And the ground setup button here allows us to modify a dielectric constant or a conductivity. And also, when you're dealing with vertical antennas, of course, radials are important, so you check this box right here. We're not going to do that in our case, since we're not going to be working with a vertical. Also notice if the ground that you're trying to model is, say for example, close to salt water, or hard rocky desert terrain, or swampy wet ground, you're going to have to look up the dielectric constant and the conductivity for those scenarios. In our case, we leave the defaults. We say OK. The material that we're going to use is going to be copper wire. You have some options here. Our End Fed Halfwave is going to be a copper wire. And the height, we're going to leave it at 1 meter. 1 meter being about 3 feet. So 3 feet off the ground. In passing, we notice that all of these entries are going to be in meters. So we need to convert from feet to meters. So let's get started. First, we're going to go ahead and say the title for our project is EFHW, or End Fed Halfwave Antenna. And then for the frequency, we are going to select 21050. You can enter the value here, but we're selecting the CW portion of the 15-meter band. Next, what we do is we highlight the X1 cell and we say enter, and we are given XYZ of 0 and X2, Y2, Z2 of 0. So here we're going to go ahead and put in some values. What values? Well, let's look at our geometry. Our field geometry, or what we expect to have, is an antenna that is going to have a 49-to-1 transformer here, a little pigtail, which is actually going to be this counterpoise, or really it's going to be the sheath of the coax cable. This is a coax cable going to our radio. The radio would be down here. This is the 67 feet long wire that I'm going to perch up on a tree. And 67 feet comes down to 33.5 in height and 58.02 feet in displacement in the x direction. You're just using Pythagoras' theorem to come up with these numbers. Again, MMANA GAL uses meters. That's the M over here in these values. So I converted 33.5 feet to 10.218 meters. Similarly, 58.02 feet comes out to be 17.68 meters. So let's go ahead and enter these values and see where we are. We leave the origin, X1, Y1, Z1 at 0. And X2, we're going to be putting in here, that one was 17.68 meters, enter. Y2, we're going to be flat against the XZ plane, so we're not going to put any Y2 displacement. And on this one, we're going to put 10.218 because that was the height, or the Z1 parameter. Let's make sure. 17.68 is our X, and 10.218 is our Z. 17.68, 10.218. So all is good. Now what we're going to do is we're going to go to View to see if this actually works the way we expect it. Well, if we look over here, we see that we have an antenna in the XZ plane. There we go. There he is. That's the X axis right there and the Z axis. So if we move it this way, you see that the antenna is with Y equals to 0. In other words, it's flat against the XZ plane back there. Great. By the way, here you can zoom, although there's not going to be too much of interest there, but you can actually zoom in here, and you can hold the shift key and move the antenna sideways up or down. So there we are. The shift key and the mouse key, of course. Okay, so are we done? Well, let's go ahead and put our feed point down here, and for that we right click and we say add the source at the beginning of the wire. And notice here now that MMANA GAL has added a little circle, a red circle right here. If we look at the legend, the red circle means that's the source. That's what we're driving our antenna with. And now if we go back to the geometry tab, there's something interesting that has happened. If you notice now, the program took that source that we just added interactively and added this thing, which is the source. On wire 1 at the beginning, a voltage of 10.0 volts are going to be used to simulate or drive this antenna simulation. Great. So now, are we ready to calculate? Well, one thing to note, we could hit start right here and the program would start calculating 21.05. We double check that we're on the right frequency that we want the simulation to run. We notice in here that it says SWR 50. So he's going to assume that your feed point has got 50 ohms of resistance. That's not what we actually have. What we actually have is a little bit different. So we want to go ahead and say setup, and here we want to change what he's going to use for an SWR of 1 to 2450. That's actually, when you use a 49-to-1 transformer, that's actually going to be your SWR. Normally you corrected that with the 49-to-1 transformer. Great. So now let's try our luck. We click start, and we end up with a very high value, 574 for SWR. And our resistance is not good, 360 ohms. So let's see if we can do something to simulate a little pigtail. Notice here we didn't put a little pigtail or the little coax going over to our radio. Let's see if we can model it. Again, how do we add an antenna element on MMANA GAL? Easy. Highlight the X1 box and click enter. Great. We leave the origin at 0, 0, 0. That's the beginning of this element. And this one, the X2, we're going to change it to -2. So what is this -2? Well, that's -2 meters, or say about 6 feet of coax going from the 49-to-1 transformer back to our radio. Let's see what the view looks like. Well, the view looks like actually what we expected it to. We can go ahead and see the little pigtail, or counterpoise as it's accurately called there. So let's go and try to calculate here. Click on start, and now we're doing a lot better. Not resistance wise, but SWR wise, we're doing a lot better here. So 2.97. Now remember, we have not added any loads. We're not modeling any loads right here. If we were, we would get, according to the legend, a little X showing up at the little feed point. We're not doing that. So what we want to do, and notice over here, there's nothing on the load section. What we want to do now is use a very interesting functionality of the program to say optimization. Notice right now we have not gone into far field plots yet. Let's hold off on going into far field plots and see if we can get that SWR a little bit better. So clicking on optimization is interesting because here MMANA GAL in a very interactive way tells us, hey, what do you want to have optimized? And what do I need to tweak to get that optimization for you? These slider bars go from least important to most important on the right. So least important on the left, we don't want that to be least important. SWR, we want to be very important. The match, not least important, we want it most important. Current, we don't care. IX or JX, as the double E's call it, we leave that at 0. Elevation, front to back ratio, gain, we'll leave everything pretty much least important except for SWR and match. And what do we want to tweak? Well, we're going to tweak the length of the wire. So let's first go ahead and see if we can tweak the length of our wire for the counterpoise. So for this, we click on type and we say there's a bunch of parameters you can optimize here, and one of them is wire. Okay, so here we do wire, and we're going to do wire 1, the X parameter. I'm sorry, that'll be wire 2 actually. So we want to change that to wire 2, which is our counterpoise. And then we're going to go ahead and say optimize, click on that one, X2. Remember, X2 was actually at a -2 meters. So that's exactly what he's going to do. So he's going to go to -2 kilometers over to 2 kilometers. Let's go ahead and put that one to 0. And then over here, I don't know, let's put that one to -50. We're not going to be doing any more than that. Step 0.01, that should be okay. So let's go ahead and start. And he is optimizing right now. He's actually done optimizing in 1.8 seconds. Do we want to save the optimization log? Nah. And now what he's done is he's gone ahead and given us actually a little bit of a worse value there. So let's go to geometry, and he's changed it over here to -3.83. So, you know, again, with optimization, you have to be careful that the mathematical solution is actually making sense. And in this case, not so much. So let's go ahead and say that we want to change that to, well, let's leave that one there, but let's optimize also wire 1. In other words, we select wire, and we're going to do the both parameters of wire 1. What are those parameters? If you remember, we had X2, which was, I believe it was 17.68, well, there it is, 17.68 meters. And the other one is the height, or Z2. Remember, that was at 10.218. So we're going to tell it, hey, not only can you optimize this pigtail, but you're also going to be able to optimize the length of our wires. And again, we're going to go here, 50, and we have to hit return or enter, and we're not going to go anything like that. So 0 to 50. Great. So now let's say start. And now he's able to optimize a few more parameters. And we notice now that the SWR has gotten a lot better. Do we want to save the optimization log? No. And the resistance is quite high, but is it? It's really going to be 2450. So it's trying to get it very close to 2450 here. So 2443 is actually a good value. We don't want this, in other words, to be 50 ohms. We want it to be what the 49-to-1 transformer is going to be able to transform down. So 1.05 sounds pretty good. But what has this actually done? Well, let's write down it's essentially run. Right now it's actually run an optimization, but nothing has been written to the file, to this session. So let's click on start, and he runs it with those same parameters, gives us the same results, but now he's actually written this information. So let's go back to our geometry tab, see what he's changed. And if you notice here, he's changed a few things. This used to be 17.68, I believe, and this used to be 10.218. So the program has optimized this length. So he's telling us to make sure these lengths are a little bit longer. So that's great. He's given us an idea. Hey, don't cut your wire exactly to 67 feet. You might want to cut it longer so that you can go ahead and make sure that it resonates well. Now, this is according to the theory. And, well, how many feet is that going to be for the length of the wire? Again, that's the X displacement and the Z displacement. So we have to use Pythagoras to go ahead and come up with the actual length of the wire, which we can do. But right now, let's continue with outputs of our program. Again, he has moved the length of our little pigtail and he's told us, hey, you probably want to make a longer pigtail. Okay, great. How long? Well, 3.8 meters. That's going on about 12 feet of coax. That may not be realizable, but we can, you know, keep that in the back of our mind. He's asking us to, the program is asking us to make a longer pigtail. And calculate, we already did this. So now if we go to the far field plots, this is interesting that he's giving us now. He's giving us an azimuthal plot over here and a cross-section plot or elevation plot over here. What is this telling us? Well, think of this azimuthal as a bird flying right over the antenna. That's the antenna high point right there, and I'm sorry, that's the origin. That's where the antenna starts, and then the bird keeps on going this way. This is the positive X direction here, and so on. So, and this over here is like you took a chainsaw to this, and you came up with the cross-sectional or the elevation profile. Why is this called the elevation profile? Because if you think about it, what you really care for dx is a low elevation. In other words, one of these lobes should be quite low. So this is telling you that you're going to have a bit of good dx going in this direction and a little bit of good dx going in this direction. Oh, hang on, what about these guys? Well, these are going to be cloud burners. What do you mean? Well, they're going pretty much straight up into the sky. So you're going to have an NVIS, remember what that is from our test. That was near vertical incidence scattering or something to that effect. So essentially that's too high, so the wave is going to go, the electromagnetic wave that from your radio is going to go straight up and pretty close to straight down. This one's going to go way out before it bounces off of the ionosphere. So that's all great, but we like to think more in terms of 3D. Well, MMANA GAL can allow that. There's 3D fast Fourier over here, and he's given us a little 3D plot. What step? Take the default, okay. And now he's giving us a pattern that we might be able to understand a little bit better. So there, right there, there's a light blue wire right there. That's the antenna. So the antenna is actually going from the origin, which is your feed point, out here to the tree. And then you see that pattern. So it's telling us, hey, you're going to have a lot of the energy going here, there, but most of it's going to be going in this direction. However, the one thing that we're interested in is this right here. So that is actually going to be a good DX pattern. And then this one over here, these two are going to be also good DX patterns. This is the cloud burning part of the antenna. So that's another feature to image the radiation pattern in 3D using pretty much software that's easy to use and it's free, MMANA GAL Basic. Now, there's one other thing to point before we call it quits, and that's the elevation. Remember we talked about an elevation of how many degrees? About 5 to 8 degrees is pretty good for DX. As a matter of fact, Callum McCormick, the DX commander, when he models his antennas using MMANA GAL, he uses an elevation of 5 degrees for DX. So we can actually set that 5-degree elevation to see what the pattern would be at 5 degrees. So you click on elevation and you click 5 and enter. So now the pattern's changed a little bit. Well, yeah, because now he's essentially taken the cross section at the 5-degree mark over here. This one over here is still pretty much a cut across, like a chainsaw took to it. But this one right here now is telling you that lobe right there, remember, the closer to the edge there, the more gain you've got, and it's actually quite good. So if we go actually and using the mouse, we can see over here now that at an azimuth angle of say minus 180, which is going in the minus x direction, you will have a gain of minus 1.8 dBi. Now the interesting thing here is that the gain is relative. So this program really gives you an idea of where your highest gain is, where your lobes are, where your highest gain is over there, and so on. So you can compare this lobe to this lobe for sure, but don't get so hung up on the actual magnitude of dBi. Remember when you see advertisements with antenna salespeople, they might say, well, my antenna's got a gain of 7 dB. Well, great, but they never tell you at what elevation, what's the actual profile. So we're getting a lot of information here. And this right here also gives you that elevation that it's saying that it's at this angle right here, you're probably going to get the best gain. And on this side over here, that's 9 degrees. So that's a good DX part of the antenna there is going to be giving you somewhat good gain, but not as good as this side over here. So that is a quick introduction to MMANA GAL. The other thing that we can do without too much effort is this is what it looks like at 15 meters. What if we were to change this to other frequencies? Say, for example, we might want to use this at 18.08, you know, at the 17 meter band. So we go ahead and do that. It gives us a 35 to 1 SWR there, so that's not so good. So don't expect it to work according to the program at 17 meters. What about 20 meters? We change that to the CW portion of 20 meters, click start, 1.45. The program is saying, hey, you might actually get this to work pretty well, according to theory, in the 20 meter CW portion. Well, let's continue playing this game. What about 40 meters CW? Click on start, 3.2. It could be worse. You might be able to actually get a tuner and actually correct for that. And then what about at the 80 meter band? Well, in that case, yeah, that's not going to work. So the antenna is not going to work so good there. And to complete this, we can actually go over to some of the frequencies to see how they would work. According to the model, it's not so good for that band either. And at 10 meters, actually it's going to go to what, according to the math, it's going to look pretty well there. So we're starting to get an idea, okay, for this completeness sake, at 6 meters. Okay, not too bad. So it's telling us that it's going to have multiple frequencies in which this is actually going to work fairly well. Having the 15 meter band, which is the one that we might be interested in, working the best. So that is a quick view of, there are other buttons, by the way. The plots buttons also gives you some information. But this is a quick view of MMANA GAL. And essentially, again, how quickly it is to enter a geometry, visualize your geometry, make sure it makes sense, make sure that your geometry in XYZ is not messed up. And then here you can also add your source, calculate. You can go ahead and click start and get the this amazing program to go ahead and calculate and give you some information. And very importantly, the optimization tab right here is the one where you tell it what you can vary given what you're really wanting to optimize for. And as a last thing, you can find out the far field plots. Again, remember, these far field plots are going to look different than what we looked at earlier because we're in a different frequency range. So remember, depending on the frequency range, your far field plots are going to look different. So this is what we're seeing right here. And another feature that we saw was the 3D fast Fourier over here for the 3D plot of our antenna. Just for grins, we can look at this one, take the default step, and you start seeing how these parameters can actually look, how these radiation patterns can actually look pretty involved. And again, that light blue line right there is our antenna. You can picture the tree being over here, sort of like what our sketch had up here, and the origin where the 49:1 transformer is being at the origin of this plot, and the little pigtail going out that way in the -x direction. So hopefully this was useful. MMANA GAL, it's a good tool, and you'd be surprised about what you can simulate with it with a few clicks, and how the program suggests things to try out. Hopefully that was helpful.